Hello, I'm Gabriel Meyer-Lee, presenting on techniques for evaluating supernets in neural architecture search. By evaluation, what we mean is understanding how neural architecture search algorithms are able to use the structure of the supernet in order to identify top-performing architectures. Previous studies have shown that supernets are ineffective as performance predictors for candidate architectures. For example, the paper How Powerful Are Performance Predictors in Neural Architecture Search by White et al. Demonstrated that performance estimates from the supernet in comparison to those obtained from other estimators do not really correlate with the benchmark performance. So, in order to explain how, despite producing these inaccurate estimates, these algorithms are able to identify top architectures, we develop statistics that can measure what sort of useful information about the architecture space actually is encoded on the supernet through the training process. Then we attempt to use these statistics in order to understand how supernet neural architecture search algorithms may be able to identify top performing architectures despite their performance estimation limitations. Now, in order to evaluate the supernet shared weights, we rely on a comparison between the rankings of candidate architectures based on validation accuracy obtained from the supernet and the ranking based on trained from scratch test accuracy from the benchmark. As a ranking comparison, this is sort of similar to Spearman correlation. However, unlike correlation, we would like to be able to measure how the similarity of these rankings varies over the course of the architecture space. So we use a cumulative measurement of the overlap in the top K architectures of each ranking. Now, in order to evaluate the architecture weights, we take the weights that are learned through the supernet training process and transform them to a probability mass assigned to each architecture, which we again view cumulatively over the architecture space. Looking at our results for the tabular NASBench 201 benchmark, we can use the sampling probability plot on the right as a more robust evaluation of the supernet training algorithm than is provided by looking at the performance of the highest weighted architecture. So, looking at these results, we see that across data sets, Dirichlet-Nas is the superior algorithm, assigning significantly more weight to top architectures. Now, viewing the top architecture ID rate, we can see results on the left. We can see an explanation for this, as Dirichlet-Nas alone is able to consistently distinguish the top architectures from lower performing architectures and distinguish between high performing architectures. For ImageNet 16120, the one data set where SNAS is assigned almost as much weight to the top models as Dirichlet-Nas, we also see SNAS able to effectively identify top architectures. Based on these results, it appears that successful supernet algorithms are able to specialize the shared weights for the top architectures in order to better identify and distinguish between them. By clustering the search space based on the similarity in architectural encodings, we can see that there are indeed, as shown by these example runs, families of high-performing architectures which are sufficiently structurally similar that they're able to obtain a distinctively higher validation performance from the shared weights. Overall, this experiment shows that despite being ineffective for predicting performance across the entirety of the search space, supernet-Nas algorithms are able to succeed by specializing the shared weights for families of top architectures in order to make relevant distinctions in performance. This insight can inform future benchmark-based NAS evaluation processes or the future design of NAS algorithms, such as those that partition or progressively shrink the search space. Thank you.